Hello everyone and welcome back to Educator.com. I'm Dan Fullerton and in this lesson we're going to talk about magnetic flux. Our objectives include calculating the flux of a uniform magnetic field through a loop of arbitrary orientation and using integration to calculate the flux of a non-uniform magnetic field whose magnitude is a function of one coordinate through a rectangular loop perpendicular to the field. Sounds complicated when you see the setup and the example problem be nice and straightforward. All right, so magnetic flux, phi sub b, sometimes you'll see it written phi sub m, describes the amount of magnetic field penetrating a surface, just like it did for electric flux. The units of magnetic flux are Webers, typically written capital W lowercase b, where 1 Weber is 1 Tesla meter squared. And just like we did previously, as we define this, we'll take a small bit of area on a surface, we'll define the normal to it, dA, going from inside to outside if it's a closed surface, and some magnetic field that's penetrating through that. So the little bit of flux that we have through that little bit of dA is going to be B dot dA, which is B dA cosine theta if we're looking for magnitudes, where theta is the angle between the normal and B. So then the total magnetic flux, phi b, is just the integral of all of these little bits of magnetic flux, d phi b, which will be the integral over the open surface of B dot dA. Same thing as we did with electric flux. When we talk about magnetic flux through closed surfaces again, normals still point from the inside to the outside. So now our total magnetic flux would be the integral of d phi b, which is the integral over the closed surface of B dot dA, which for magnetic flux is going to equal 0. Let's talk about that.